Okay, let's now complete the proof that the closest points between the convex hulls of two linearly separable sets yield the optimal margin classifier. So just to pick up where we were, remember the basic picture, which is that we have the green points and the blue points. Here they are, and we have their convex hulls. And we find the closest points between their convex hulls, and we take the perpendicular bisector, and that's the optimal margin classifier. What we know so far is that you can actually find these closest points, and that having found them, the vector that runs from P to Q is unique, even though the points themselves may not be unique because the two convex sets could have parallel sides. Okay, so let's pick 2 points, P and Q, in the positive and negative linearly separable sets, and assume they have the minimum distance. And we're going to let W be the vector which runs from P to Q, and we're going to let B plus be W dot P and B minus be W dot Q, and consider the two hyperplanes F plus or minus X, which is W dot X minus B plus or minus. These are the two hyperplanes. Let me use a different color just for fun. These are the two hyperplanes in my little tiny diagram here, which run through the closest points and are parallel, have the same normal vector as the vector joining P to Q. So we already know that if you compute if these were supporting hyperplanes, in other words, if they did actually have the property that the convex hulls lay on either side of them, then the associated margin is given by the formula tau W of between A plus and A minus is B plus minus B minus over the norm of W, and that's going to work out to be P minus Q. And in fact, I think that's clear. We might as well just settle that part, because this is, by definition, B plus is W dot P and B minus is W dot Q. So this is W dot P minus Q over the norm of W. But W is P minus Q. So this is the norm of W squared over the norm of W, which is the norm of W, which is P minus Q. In other words, we will have shown that the margin is, for this particular W, is equal to the distance between P and Q, but we already know from our earlier work that that's the best we could hope for. So this would be the optimal margin. So the crucial part of this result is that these hyperplanes are in fact supporting hyperplanes. So let's prove that. And let's work with F plus. And so we have our convex hull, and we have our point P, and we have our hyperplane, and F plus equals W dot X minus B plus equals 0. If this isn't a supporting hyperplane, then there has to be a point in the convex hull where, call it P prime, where F of P prime is negative. We already know that it runs through the point P. We constructed it that way because B plus is W dot P. So F plus of P, which is one of these closest points, is 0. So to be a supporting hyperplane, there are two conditions. Everything has to lie on one side of you, except you have to pass through at least one point. So if it's not a supporting hyperplane, it means there's a point that's on the wrong side. Some point P prime lies on the wrong side of this hyperplane. So let's do an argument using convexity, which is very similar to what we did before. Namely, we're going to consider the line segment. So here's our picture. Here's our hyperplane. Here's P. Here's the positive side of the hyperplane. And here is P prime, which lies on the wrong side of it. And we're going to consider the line which runs from P to P prime. And meanwhile, over here, we have Q, which is the other point, so that it's in C of A minus, and this distance here is minimal. Now, by assumption, this picture is a little confusing. By assumption, we know that this point is supposed to also lie in C of A plus. That's our hypothesis that we're going to contradict. And so by convexity, this whole line segment, which I'm calling T of S, also lies in C of A plus. So maybe you can anticipate the problem here. If this is supposed to be the closest point that could possibly be to Q in C of A plus, and this point is on the wrong side of the line, then it seems impossible that some point on this segment isn't closer to Q than P prime. So that's what we're going to show, and it's similar to the argument that we did before, namely we consider the squared distance from T of S to Q, and we take its derivative. So d of 0, since T of 0 is P, that's the minimum distance squared, and d of 1 is P prime minus Q squared. And this has to be bigger than or equal to d squared. And in fact, it has to be the case that if we draw the picture as I did before, here's 0, here's 1, here's d squared, it has to be the case that T of S is bigger than or equal to d squared for all S between 0 and 1, because all of the points lie inside C of A plus, and d squared, the initial value, is the smallest possible value. So you can probably see where this is going to go. We take the derivative of this function, and we get, so remember what it is. It's T of S minus Q the derivative of this is 2 times T of S minus Q times the derivative of T of S. Q is a constant, but the derivative of T of S, remember what T of S is, the derivative of T of S is P prime minus P. So this is 2 T of S minus Q dotted with P prime minus P. And if you evaluate that at S equals 0, you get T of 0 is P minus Q times dotted with P prime minus P. And of course, P minus Q is W. So this is 2W dotted with P prime minus P. And remember that W dotted with P prime, that F plus of P prime is W dotted with P prime minus B plus. So W dotted with P prime is F of P prime, F plus of P prime plus B plus, and W dotted with P is F plus of P plus B plus. But of course, this is just 0 because F plus of P is, F plus of P is 0. And so these B pluses cancel out. And so this is 2 F plus of P prime. And we're assuming that P prime is on the wrong side. So we're assuming that this is less than 0. And that gives us the same contradiction we had before, because our function, as I drew in the picture, is supposed to start at d squared and stay above d squared. But if it starts out with a negative derivative, then it's going to have a point to the right of 0, which is less than d squared, and that contradicts the minimum distance condition. And the same argument would give you the same result for F minus. And so this shows you that F plus and F minus are supporting hyperplanes. And then just to recap, since we knew that they're supporting hyperplanes, the margin calculation that I did at the beginning gives you that the margin is equal to P minus Q. We know that's the best you can do. And so we have found the optimal margin in terms of the closest points in the convex hulls.